Chemistry is more than just wearing lab coats, safety goggles, and mixing beakers. It can feel like magic sometimes. A realm where things don't follow the laws, colors move like they're alive, and metals hold memories. I'm Mike with List 25, and today I'm looking at 25 chemical reactions that broke reality. But before we begin, as always, don't forget to like, share, comment, subscribe, click the notification bell so you don't miss out on any new content. All that truly helps the channel. With that being said, let's go mix things together. Oh, I should have said let's mix it up. 25. Wöhler's Urea synthesis. People thought organic substances were exceptional until Friedrich Wöhler heated ammonium cyanate and made urea. According to the dominant theory of the time called vitalism, living creatures had some kind of life force that let them make organic chemicals. Non-living things couldn't. When Wöhler accidentally synthesized urea, a compound found in urine from a purely inorganic salt, he tore that belief to shreds.
To shreds, you say?
Suddenly, it was clear that life chemistry was just chemistry. This was more than just a technical achievement. It shook the world of ideas. Vitalism fell apart. The implications were massive. If organic molecules could be built in the lab, maybe life itself could be understood as matter and reactions, not magic. Wöhler's discovery was the crack in the dam that eventually let modern biochemistry flood through. The funny thing is, he wasn't even trying to start a revolution, but science rarely asks permission. 24. Radioactive decay. Henri Becquerel wasn't searching for something reality-bending. He just wanted to see if uranium salts glowed after sunlight exposure. What he got was stranger. The photographic plates he left in a drawer with uranium still fogged up, even without sunlight. The uranium was emitting something all on its own. Later, Marie and Pierre Curie dug deeper and separated radium and polonium. This showed the world that atoms weren't solid, immortal marbles. They could be split apart and release particles and photons that we can't see. This finding destroyed the traditional belief that atoms couldn't be broken down. It broke apart nuclear physics and transformed how people use energy forever. There was a hidden engine of power and danger inside every rock and every element. It's wild to think that this revelation began not with a grand experiment, but with uranium salts sitting in the dark, quietly betraying the secrets of the atom. 23. Nuclear fission. When Otto Hahn and Fritz Strassmann bombarded uranium with neutrons, they didn't expect to split the atom in half. But that's what happened. The uranium nucleus broke into lighter elements, which let out a huge quantity of energy. Lisa Meitner and Otto Frisch correctly understood the data and explained nuclear fission, which is when one nucleus breaks into two. The amount of energy released was what made this so mind-blowing. E equals mc squared was no longer just a smart equation, it was a reality that changed the world. It was now conceivable for chain reactions to happen. This was the discovery that made both reactors and atomic bombs possible. Humanity had gone from lighting fires with wood to splitting atoms for energy in just a few centuries. And unlike Wöhler's harmless urine experiment, this reaction literally changed geopolitics and global survival. The atom wasn't just matter anymore. It was power. 22. Cold fusion claim. Picture scientists at a press conference stating they had made nuclear fusion happen at ambient temperature. In 1989, that's exactly what Martin Fleischmann and Stanley Pons did. If true, it would have meant limitless clean energy without giant reactors or the sun's crushing pressures. Reality? Not so much. Their discovery couldn't be consistently replicated, and the claim crumbled under scrutiny. Still, for that brief, shining moment, the world believed we'd cracked the ultimate code: infinite energy in a glass of heavy water. This wasn't a chemical reaction, but the fallout left the scientific community embarrassed and cautious, but also showed just how hungry people were for breakthroughs that rewrite the rules of physics and chemistry. Cold fusion still lurks at the fringes of research, with some diehards chasing it decades later. Even if it was a scientific mirage, it stands as a story of how badly we want reality to bend. 21. The Belousov-Zhabotinsky oscillator. Most of us learn that chemical reactions head toward equilibrium and stop. But Boris Belousov stumbled upon something that didn't follow the rules. He mixed a few compounds, and instead of stabilizing, the solution changed colors back and forth. Clear, yellow, red, cycling like it was alive. At first, no one believed him. A reaction that pulsed and oscillated? Well, that sounded impossible. Anatol Zhabotinsky later expanded on the work, showing that self-organizing chemical systems are very real. The Belousov-Zhabotinsky reaction looks like liquid magic, a potion with its own heartbeat. But beyond the cool visuals, it was profound. Chemistry could create order out of chaos, cycles out of randomness. That idea went to biology, where oscillations are what make the heartbeat and the circadian rhythms happen. Belousov's work wasn't merely a spectacular drama in the lab, it was a glimpse into chemistry's hidden ability to organize itself. 20. Superconductivity. Imagine that electricity could flow forever without any resistance. Heike Kamerlingh-Onnes was the first person to see superconductivity when he cooled mercury to near absolute zero. He expected resistance to drop, but to hit zero? That was unthinkable. Superconductors only worked at very low temperatures for decades, making them a lab curiosity. In 1986, scientists detected high-temperature superconductors in ceramics. It wasn't just a hypothesis anymore that cables could never lose electricity. Magnetic levitation trains, sophisticated MRI equipment, and electronics that looked like they came from the future all became possible. The reality-bending part? It was previously beyond the purview of classical physics to explain. The puzzle was only solved by quantum physics, which demonstrated that electrons can pair in unique ways. The idea that cooling may completely alter a substance's electrical properties broke expectations. Superconductors remain one of the most unusual and exciting fields of chemistry and science. They suggest there may come a time when energy waste is no longer a problem. 19. Superfluid helium. If superconductivity makes electricity flow forever, superfluidity does the same for liquids. When helium is cooled near absolute zero, it stops behaving like any normal fluid. It flows without viscosity. It climbs up the walls of the container. It seeps through microscopic cracks. Imagine a liquid that refuses to stay put, sneaking out of any bottle, moving like a ghost. Piotr Kapitsa, John Allen, and Don Meisner documented this surreal behavior in 1937, and it blew open the field of quantum fluids. Classical physics had no words for it. Superfluid helium showed that quantum mechanics wasn't confined to the tiny world of particles. It could spill into something you could see and touch. Watching liquid creep up and over the rim of a beaker isn't just unsettling. It's like reality itself is leaking. Chemistry had birthed the liquid that broke the rules of matter. 18. Ozone hole chemistry. Chlorofluorocarbons, or CFCs, were once hailed as miracle chemicals. Stable, non-toxic, perfect for refrigerators and spray cans. Too perfect, really? Scientists like Mario Molina and F. Sherwood Rowland discovered that these supposedly inert compounds drifted into the stratosphere where ultraviolet light cracked them open. The chlorine atoms that were released could break down ozone molecules in a cycle that keeps going. This was a stunning turn of events. Something safe on the ground was breaking down the Earth's protective shield above. The discovery of the ozone hole over Antarctica in the 80s shocked the world. A reaction no one expected was quietly rewriting the atmosphere. Thankfully, the world responded with the Montreal Protocol, banning many CFCs, one of humanity's most successful environmental interventions. But the lesson remains. Inert doesn't always mean harmless. Chemistry doesn't care about labels. Under the right conditions, even a fridge gas can punch a hole in the sky. 17. The Briggs-Rauscher oscillating reaction. If you ever want to convince someone chemistry is magic, show them the Briggs-Rauscher reaction. You mix some hydrogen peroxide, iodate, malonic acid, and a catalyst, and suddenly the liquid starts flipping colors, clear to amber to deep blue, over and over. It's not a one-time flash. It cycles like clockwork, mesmerizing anyone watching. Discovered by Thomas Briggs and Warren Rauscher, it became a staple science demo because it feels alive, like the liquid is breathing or thinking. But it's not just eye candy. This oscillating system helps scientists understand nonlinear chemical dynamics, reactions that don't just slide smoothly to equilibrium, but bounce, swing, and repeat. It turned chemistry from something static into something rhythmic. If the Belousov-Zhabotinsky reaction was the proof, Briggs-Rauscher was the showstopper. Watching it, you can't help but think, chemistry doesn't just build matter. Sometimes it performs. 16. Chemiluminescence. Who doesn't love glow sticks? Snap one, shake it, and suddenly light pours out with no heat, no flame. That's chemiluminescence. Molecules releasing energy as visible light during a chemical reaction. Fireflies do it naturally, with luciferase enzymes triggering light-producing chemistry in their abdomens. Humans figured out synthetic versions, creating safe, portable light for everything, from kids' parties to military operations. The wild part is the efficiency. Most light sources waste energy as heat, but chemiluminescence converts chemical energy almost entirely into photons. When first studied, it felt like molecules were breaking the rules, conjuring light out of nowhere. It blurred the line between biology and chemistry, between glow bugs and glow sticks. There's something uncanny about holding a tube that suddenly glows like it's captured a star inside. Light without fire used to be in the domain of myth. Now it's just a snap away, thanks to chemistry. 15. Fluorine reactions. Fluorine isn't just reactive, it's feral. Henri Moissan first isolated it in 1886 after decades of failed, often deadly, attempts by other chemists. Once he had it, scientists quickly learned that fluorine will attack almost anything. Glass, steel, water, flesh. Nothing is safe. It can even coax noble gases, once thought untouchable, into forming compounds. Fluorine chemistry blew up the idea of inertness. If even helium and xenon could be dragged into reactions, the periodic table wasn't as rigid as people thought. At first, fluorine seemed too dangerous to be useful, but taming it led to materials like Teflon, which resists sticking in heat. Fluorine's wild side also gave us powerful refrigerants and pharmaceuticals. Its discovery was like finding a dragon. Terrifying, uncontrollable, but eventually harnessed for everyday life. Chemistry had revealed an element that lived up to its lethal reputation. 14. Sodium in water. If you've ever seen sodium drop into water, you'll know it's not subtle. The metal skitters, hisses, then bursts, sending sparks and flames flying. In reality, sodium tears the oxygen from H2O, generating hydrogen gas, which catches on fire in the heat. It's so fast, it looks like the water itself is on fire. Early chemists were stunned by the sheer ferocity. The reaction showed how wildly different elements can be from each other. Sodium, soft enough to cut with a knife, becomes a miniature bomb the moment it touches something as ordinary as water. The spectacle is so dramatic, it remains a classic classroom demo, one that reliably gets students' attention. Sodium's furious love affair with water is a reminder that chemistry is more than just numbers on a page. 13. Blue bottle reaction. Shake a clear solution and it suddenly turns deep blue. Let it sit, then it fades back to clear. Shake again, and the cycle repeats. That's the blue bottle reaction, the classroom favorite that feels like a magic trick. What's happening is a redox reaction involving methylene blue, glucose, and oxygen. Agitating the solution brings oxygen, which turns the dye blue. As the glucose reduces it, the color fades back. The cycle continues until the reactants are used up. When first demonstrated, it defied expectations. How could a chemical solution seem to recharge itself? It taught scientists, and students, about reversible redox reactions in a way that's unforgettable. But beyond the science, there's something charming about it. Chemistry usually looks permanent. Once it changes, well, that's it. But here was a bottle that seemed to breathe, a liquid with moods. 12. Thermite reaction. The thermite reaction looks like chemistry's answer to a volcano. Mix aluminum powder with rust, iron oxide, light it with enough heat, and you unleash a torrent of molten iron at 2500 degrees Celsius. The reaction is brutally simple. Aluminum steals oxygen from iron. But the energy released is so intense that the products glow white hot, easily cutting through steel. First discovered in the 19th century, thermite became a practical tool for welding railroad tracks and destroying enemy equipment in war. It's amazing to see a pile of powder turn into a waterfall of fire and liquid metal in just seconds. Thermite showed how chemical bonds may hold a lot of energy that's ready to be released when the correct reaction happens. It's a reminder that chemistry isn't just about molecules moving quietly. Sometimes it's about unleashing raw, blinding fury from the most ordinary materials. 11. Phlogiston. Before modern chemistry, scientists believed in phlogiston, an imaginary substance that supposedly escaped when things burned. It explained fire, or so people thought. But experiments kept poking holes in the theory. Antoine Lavoisier finally put an end to it in the late 1700s. He demonstrated that combustion does not involve the departure of material by meticulously examining the masses during the process. It was about oxygen combining with fuel. The weight actually increased, not decreased. This was more than just a correction. It was the birth of modern chemistry. The previous mystical explanation was thrown out in favor of a clear, testable framework. Lavoisier's research demonstrated that reality does not congeal phlogiston-like apparitions, but rather tangible and quantifiable processes. It changed science from guesswork to accuracy, and chemistry from alchemy to a field with rules. Watching a centuries-old worldview collapse was dramatic proof that evidence trumps myth every time. 10. Elephant's toothpaste. Put hydrogen peroxide in a container, add a catalyst like potassium iodide, and all of a sudden, foam starts to rise in a huge column, flowing out like someone squeezed a tube of toothpaste. The elephant's toothpaste reaction is pure spectacle, beloved by science communicators. What's happening chemically is the rapid decomposition of hydrogen peroxide into water and oxygen, with the soap trapping the gas into bubbles. It's safe enough for demonstrations, with precautions, but dramatic enough to look dangerous. The sheer volume of foam from a small amount of liquid feels like a magic trick. But it also illustrates catalysis, how adding the right helper speeds up a reaction dramatically. When first shown, it challenged the intuition that reactions just plod along at fixed speeds. In reality, with the right chemistry, reactions can leap forward in spectacular fashion. Sometimes science really does blow up in your face. 9. Shape memory alloys. Imagine bending a piece of metal into a wild shape, then watching it snap back into its original form when heated. That's the magic of shape memory alloys like nickel titanium. Discovered in the 60s, these materials undergo a phase change at certain temperatures that lets them remember their original structure. At first glance, it feels like metal with memory, a substance that refuses to stay bent. Scientists quickly realized its potential for medical devices, robotics, and even eyeglass frames that return to shape after being twisted. The discovery blurred the line between chemistry, physics, and science fiction. Metals weren't supposed to behave like rubber bands, but here was an alloy rewriting what solid meant. Watching one of these wires twist back into its factory-set shape still feels uncanny, like the material is alive. Reality bent and then straightened itself out again. 8. Polymerase chain reaction. Kary Mullis's invention of PCR changed biology overnight. The idea was deceptively simple. Use a heat-stable enzyme from bacteria to copy DNA over and over exponentially. What seemed impossible, making billions of copies of a gene in hours, became routine. Before PCR, analyzing DNA was slow and limited. After PCR, genetics exploded. Forensics, medicine, ancestry, disease research, all unlocked by this technique. What made it so stunning wasn't just the speed, but the audacity. Mullis called it obvious in hindsight, but at the time it was revolutionary. Chemistry and biology merged into a machine for amplifying life's code. PCR felt almost like cheating reality, taking the slow copying of DNA that happens in cells and turbocharging it in a test tube. Suddenly, humanity had a photocopier for genes. One reaction, and the biological world was never the same. 7. Enzyme Catalysis. Enzymes are proteins, but they don't act like passive structures. They're catalysts, chemistry's speed demons. Some reactions that would take centuries in a test tube happens in milliseconds in your body thanks to enzymes. What first defied understanding was how much faster enzymes made things happen. Millions of times faster. It felt impossible. How could a glob of protein twist and turn molecules with such precision? The answer is in their complex forms, which have evolved to direct certain reactions with almost magical precision. The discovery of enzyme catalysis ended the previous notion that chemistry had fixed rates. Instead, life had built-in accelerators everywhere. Without enzymes, life as we know it couldn't exist. They're the quiet magicians inside every cell, proving that speed in chemistry isn't about brute force, but finesse. Watching enzymes at work is like glimpsing nature's cheat codes in action. 6. Photosynthesis. People often forget that plants turn sunlight into nourishment. Scientists began to understand photosynthesis in the 20th century, which made it seem like they were defying the rules of nature. Photosynthesis uses light energy to split water into oxygen and electrons, and then uses those electrons to transform carbon dioxide into sugars. It's one of the most beautiful and complicated chemical dances there is. For centuries, people assumed plants just ate dirt to grow. Finding out that they could trap light and turn it into fuel was like finding out that they ran on bottled sunshine. This mechanism is responsible for the presence of life on Earth. It sustains ecosystems, oxygenates the air, and alters the atmosphere. It used to seem crazy that molecules could catch light and turn it into sugar, yet that's what every leaf is doing, quietly rewriting reality one photon at a time. 5. Haber-Bosch process. Pulling nitrogen straight out of the air sounds like a wizard's trick, but Fritz Haber and Carl Bosch made it a reality. Nitrogen gas makes up most of Earth's atmosphere, but its triple bond is notoriously unbreakable. Haber discovered a way to smash it apart using high pressure, high temperature, and a catalyst, producing ammonia. Bosch scaled it up to industrial size. The result was artificial fertilizer, unlocking a food supply that could feed billions. Before this, farmers could only obtain nitrogen from natural sources, like dung or guano. The Haber-Bosch process broke the rules of nature by making the atmosphere give up its nitrogen. Some call it the most important invention of the 20th century. It allowed humanity's population to explode. Yet, it's also a double-edged sword, since the same chemistry fuels explosives. Air turned into bread and bombs. 4. The Teflon Accident. Sometimes reality breaks by accident. In 1938, Roy Plunkett was working with a gas called tetrafluoroethylene, storing it in cylinders under pressure. One day, he opened a tank and found the gas had vanished, replaced by a slippery white solid. Instead of being ruined, the experiment had stumbled onto polytetrafluoroethylene, better known as Teflon. This new polymer was bizarre. It was incredibly inert, resisting heat, sticking to nothing, and immune to most chemicals. At first, no one knew what to do with it. But over time, Teflon made its way into cookware, wiring, medical equipment, and even space technology. It was a chemical outlier because its bonds were so strong that it was almost impossible to break compared to other polymers. What began as a failed gas experiment became one of the most useful, reality-bending materials of the modern age. A mistake turned into a miracle. 3. Perovskite solar cells. Solar panels have been around for decades, but in 2009 scientists tried something unexpected, a class of crystals called perovskites. These oddball materials suddenly showed solar efficiencies far higher than expected, rivaling silicon, and they were cheap and easy to make. The chemistry seemed almost too good to be true. Traditional solar materials took years of careful engineering to inch forward in performance. Perovskites leapt ahead in months. They broke the unspoken rules about progress in solar science. Researchers were shocked and rushed to find out why these hybrid organic-inorganic crystals were so good at collecting light. Perovskites opened up a completely new approach to generate renewable energy despite ongoing stability issues. Once again, chemistry revealed that a humble compound could upend an entire industry. It felt like sunlight itself was conspiring with scientists to bend reality toward a cleaner future. 2. Quantum tunneling in enzymes. Classic chemistry says particles need enough energy to get over reaction barriers, but enzymes sometimes cheat. They use quantum tunneling, letting protons or electrons jump through barriers instead of climbing over them. This is the best example of breaking the rules on a small scale. Biology was no longer just using smart designs and active sites. It was now incorporating the craziest notions from quantum mechanics. Scientists were surprised to discover that quantum tunneling is a natural phenomenon. It altered people's perspectives on physics and biochemistry in ways they couldn't have predicted. Enzymes were more than simply molecular motors. They were gateways to quantum weirdness, which made things that shouldn't happen all the time inside cells. The fact that you're alive right now owes something to particles that occasionally skip through barriers like ghosts. It's chemistry colliding with physics at the strangest, most fundamental level. Life, it turns out, is sneakier than anyone thought. 1. Miller-Urey experiment. Stanley Miller and Harold Urey sought to see if an absurd hypothesis might work. Could the building elements of life grow in a primordial soup that had no life? They mixed water, methane, ammonia, and hydrogen, gases thought to resemble early Earth's atmosphere, and zapped it with electricity to mimic lightning. After a week, the brew was full of amino acids, the raw materials of proteins. This shook the world. It said that the chemistry of life may start on its own if the necessary conditions were met, without any help from God or the universe. Life no longer seemed like a miraculous exception. It seemed like a probable result of chemistry itself. While later studies redefined the recipe for Earth's early atmosphere, the Miller-Urey experiment remains iconic. It cracked open the possibility that biology is written into the rules of matter. And that's all I have for you today. But before you go, how about some bonus trivia? Wöhler's accident wasn't a total accident. He was actually trying to make ammonium cyanate crystals prettier. The urea product was an unexpected side effect. Well, now that's it for today. Actually, wait. There are some substances created through these chemical reactions that are very dangerous. Check out this video for that. And as always, make sure to like, share, comment, subscribe, notification bell, and I'll catch you guys next time. See ya.